right, so I'm going to be talking about my recent experiences with manufacturing automation, specifically candle manufacturing. So I am a software engineer. I have no previous experience in this area. I haven't done any kind of manufacturing stuff for automation like this before. But this opportunity came around and it seemed fun, so I said yes. And I got pretty much all the creative control over these decisions. And so I kind of did what basically anything I needed to. I didn't follow any kind of industry standard approach, as you'll see. I'm going to start by describing my first solution with MicroPython and how that led to what I'm currently working on, which is a series of generic composable PCBs that can be interconnected to automate this kind of problem. So we're specifically automating the wax filling of these candles. This is a picture of the wax filling setup. So on the top we have 3 large tanks. These tanks are used to melt the wax. From there, the wax is dispensed into an intermediate heated wax hopper. And from there, it's dispensed into the glass jars with pneumatically actuated valves. The glass jars wind underneath on a conveyor. Each row has 4 of them. So here's how you operate this thing manually. This is how it's done now. The operator moves the lever up to move the conveyor forward, positions the jars in place. They pull the lever down and it dispenses wax, fill up the jars. Then you may need to wait a little bit because sometimes it's like yarn or something gets stuck in the valves and it dribbles and it can dribble over the jars and get messy. So you just wait a bit and then you repeat. And sometimes you may need to adjust the valves to dispense wax into large tanks into the small hopper to fill that up. And that's it. So that's what we're automating. The algorithm for automating this, what our machines can do, is basically the same thing. It's a few different steps. First, turn the conveyor on to move the jars into place. We're detecting the position of the jars with a line break sensor. This is a sensor that's similar to the kind of sensor you find in a grocery store on the conveyor there that detects your groceries and stops the belt. When that's in place, we dispense wax for some determined amount of time. And then for the drip, we wait a little bit, just do nothing. And then repeat, move the conveyor to the next jar. Before we can move to the next jar first, we have to move the conveyor, we have to move the jars that have just been filled out of the way of the sensor before we can repeat the cycle. And then it's important to also maintain a constant wax level in the hopper because we're dispensing the wax into the jars at a fixed time period. The flow rate needs to be constant, and so the level in the hopper needs to be the same at all times. This was all programmed in MicroPython. I'm still sometimes feeling the need to justify this decision. I'm not going to do it right now, but perhaps later you can come talk to me about it. This was automated mostly with like pneumatic solenoid valves, shuttle valves, basically very simple pneumatic equipment. Everything was installed in parallel to the manual operation, so if it breaks, something goes wrong, you can still operate the system manually. For the wax level control, there's a float valve in the hopper, reads the level, so you can tell when the level goes down, and then you can open up one of the valves from the big tanks. Each tank has a pneumatic piston valve installed on it. And yeah, you select one of the tanks at a time, and that's the one that drains, and you can select a different tank and so on. So these are the sort of design goals that I had in mind when I was writing software and designing this solution. I think these are all kind of, in a sense, obvious. Like, who doesn't want a reliable system, right? Who doesn't want to be able to debug and fix it? It's something you really want for everything that you're building. But in this case, it became really most of the problem for me. The actual logic we just saw, it's really quite simple. Normally when I'm working, I work for a large company, and all the software that we write, like for our customers, if that breaks, if they have a problem with it, and I'm not around, that's not a problem at all. Because there's a whole team of people that can take care of it, that can fix it. And that's not the case here. In this case, I'm like kind of solely responsible for it, and there's a lot of the system that the people just don't understand. They understand a lot of electronics and pneumatics and mechanics because they're mostly hands-on fixing it. They don't have a dedicated engineer. But when I come in and I write a bunch of software for them, there's this big chunk they just don't get anymore, and I'm responsible for that. And there's a whole opportunity to leave them in a really bad position if that goes wrong. Yeah. So I thought when I started this software was going to be very short. It seems like it would be really short, right? But in the end, the way that I interpreted these goals, the way that I became afraid of everything that could go wrong, I ended up writing a lot of code for it. So for example, what if the code gets stuck in a loop somewhere? So you open up the valve for one of the tanks, your code crashes, it goes in a loop, something goes wrong with the sensor, it never escapes. And this valve is open, and it's spilling wax all over the floor, and it happens at like 6 a.m. before anyone shows up, so you spill thousands of pounds of wax everywhere. And then I get a call when I'm in like vacation somewhere in Thailand, and it ruins everything. So I designed the software so that there is no loops anywhere. There's the single top-level loop. So there's no part of the software that could steal all of the CPU time. Stuff like this that I hope to sort of like get some confidence that that things would keep running, even if things go wrong, it wouldn't go catastrophically wrong. To make things debuggable, I added the ability to test every specific component of the system. So if it breaks, you can check one by one each part and see that it is working, that it's okay, and it can hopefully isolate the problem and fix it. And that in the end, I think I wrote something around 1,000 lines of code for this, which normally wouldn't be a lot, but in this case, it seems like a lot for what it is. But I kind of accepted that, made peace with it, and moved on. I think one of the areas where you end up with a lot, where the code kind of grew is that because there's a lot of like modes and debug stuff, I put a screen and LCD in there with a menu so you can select all these options, all these different modes, test all these different things, view all the different states. I have an application framework to sort of manage everything. But in the end, that seemed like it was okay for a bit. So this is one of the first setups, the first tests. In this case, at this point, it was not using a line break sensor. You can see this sensor is kind of propped up with the wire there by the jars. That is an infrared reflectivity sensor. The idea is that it senses the curvature of the glass as it passes and can stop it at that point. Because at this point, all the jars are kind of jammed together, and they are varying distances away from the edge of the conveyor, because they're all just kind of put on there by someone. So you couldn't use a line break sensor. But since then, we changed it so there's a gap in between it, and that simplifies a lot of things. This is a little bit later version mounted inside of an enclosure panel. You can see the MicroPython board, the display. So I was contemplating the size of this software at some point because it just didn't quite feel right. And I realized that, first off, this float switch, the way that I'm maintaining the level, the software is basically just routing the value that it reads from the float switch to a pin for whatever selected tank. So it's just that's what the ISR is doing. It's basically just acting as a dumb switch all the time. And if that one pin is high, it raises the other pin high. The software itself does other problems. Or is it okay? Yeah. The software itself does other work. Like, there's an option to select which tank you want to use. There's an option to manually test it, to open up that valve, to manually run it. There is, on all the other different pages, on other different modes, there's often it displays which tank is active, whether or not the valve is open, stuff like that. But this can all be replaced with hardware, with a few switches. One switch to select if it's even on, to switch it to manual or to switch it to auto. Another switch to select which tank you want to use. And that's basically it. And I think this is better for basically every reason I can think of, almost. First off, this is kind of a separate control system, so it's isolated from the software now. The software, the CPU can crash, anything can go wrong with that, and it doesn't matter. This continues to run, it continues to work. It's unaffected by that. It's isolated, and that's generally a good thing. It's also, the interface is easier to use. Before you have to go through a menu and you have to select which tank you want. You have to go to another part in the menu to turn that valve on. And I don't think there's anything more intuitive than a button, like a little switch you can flip. It's very easy to read, it's easy to use, you don't have to tell anyone how to use it, it's obvious. It's easy to see from far away, you have bright LED when it's on and when it's off. So naturally, this kind of, the experience of having to like take so much code and delete it and replace it with some wires and 2 switches, it's like, it's hard, man. and it's a little embarrassing. So I started to think about how I would redesign this whole system if I couldn't write software for this, if I had to go back in time to the point at which before I learned how to code, like what would I come up with? How would I do it? So I started thinking about these devices. These are some of the things that I purchased for like little automation things, little common automation products. The first 2 are just timers. The second one is a temperature PID controller. There's a lot of products like these, but I think what I felt was missing was a way to sort of put everything together, to sort of interconnect everything in a way that I could use it to solve more complicated problems, and to have it be in a form factor that wasn't, like this and could easily work and would look kind of semi-professional and so on. So what I came up with is what I'm now calling control bricks. These are a collection of PCBs, of composable PCBs that you can interconnect into a long series that can be used to solve this kind of automation problem. And the idea is that once you connect it, it's kind of in a way like software. It runs kind of like software. When a block is triggered, it becomes active. It executes its function, whatever that is, very simple function. Once it's done running, it passes control to the next one. That one runs, passes control to the next one, and so on. And I think the greatest benefit to this sort of approach is that each one of these pieces is really very simple. It's very easy to understand what each piece does. And there's just no application level software, no application specific software, which I think is very important. And I think that's really empowering to the people that have to maintain this kind of a system. They're freed from all the problems that you get when you have a custom software custom one-off software. It enables you to not just debug whether or not the sensor is working, but it enables you to debug the entire thing. There's no like black box here that you don't understand. So so each one of these control bricks has a set of common inputs and outputs that enables you to connect them together. The in and the out, there's 3 pins right now that enables you to pass the ground and the power between them, and the trigger line. Most of these blocks also have an active connection, and that connection goes high when the block becomes active while it's executing whatever function it's responsible for. That's used to connect to some actuator, the relay. That's what would power the conveyor or open a valve, something like that. Some of these blocks can have sensor inputs as well. So I'm going to look at each block individually. This is the delay block. It's used for pausing or sleeping for some set period of time. It has this rotary encoder that enables you to configure how long it's going to sleep for. When it's not active, it displays how much time is configured. When it is active, it counts down on the display how much time is remaining. Every one of these blocks is right now using one of the 18 mega chips from the Arduino Uno. There is I think, good reasons for using that in this sort of situation. I don't know if I'm going to keep using it. The main reason that I used it is because I have a bag of them at home that I've had for a long time, so this was good. Every block also has a button by the active output that enables you to manually trigger that output to test if the sensor or whatever you're actuating actually works. The while brick has a sensor input, and this pauses kind of like the delay block does, but it remains paused until it matches the selected condition. Right now this is done with a jumper cable, so you can select high or low. When it no longer matches, it's going to continue. It's going to pass control onto the next block. It's going to finish. The count block simply increments a counter. It gives you the option to reset it. And every one of these sequences of blocks needs some way to start and stop it, and that's what the run block does. When you first hit the button on the run block, it emits a trigger pulse to start the chain, so the next one starts executing. The block itself goes into active mode. While it's active, it will forward the trigger pulse that it receives, just basically pass it along, and that enables you to create loops of these blocks that will keep executing around and around until you hit the button again and then it turns it off. At that point, everything keeps running, but it's kind of like a graceful shutdown. It will just not continue to iterate. If you want to like force panic, shut this thing off like the big red button, you need to kill the power. There's no other way to do it right now. And the relay brick I haven't made because I just ended up buying these cheap ones offline. But in the future, I think I'm going to make one so to have an indicator on it. Otherwise, because you can trigger one relay from multiple bricks and there's no one spot to see if, example, that relay represents the conveyor being on. There's no other way to see that, one single spot to see that it's on or off. So those are all the bricks that I've made. There's obviously many that you could make, but those are the ones I need for this particular solution. So now that we have all these pieces, we can actually assemble them and build this solution. We can see what that would look like. This is that machine algorithm from the earlier slide. I've just copied it here. Add an extra line to increment the count as an excuse to use the counter block. So first step, we want to move the jars forward. So we use a while brick. We connect the active output to the conveyor relay and have the jar sensor to the input and select that block. We select the condition to be low so that the relay is going to be on while there's nothing blocking the jar sensor. Next step is to delay. This allows us to configure the wax dispense time. Connect that to the wax dispense relay. And then we need to delay again for the dribble. So that's an optional delay, connected to nothing because it's only responsible for just waiting there a bit. And then we need to move the jars that have been filled out of the way of the conveyor, or out of the way of the sensor. So we have another while brick, except we've selected the condition to be high. So it's going to be, while the jar is blocking the sensor, it's going to be high. It's going to move it out of the way. It has the same connections as the previous while brick, as the first one. The only difference is that the condition is inverted. And add the count brick so we know how many iterations we've gone through, if we care about that. Add the run brick so we can start and stop this thing. And we connect the output trigger of the last block to the input of the first one, and this allows this whole thing to iterate in a loop again and again. And here is the complete solution assembled on my kitchen table. Looking at this, I can immediately see that it has been configured to dispense wax for 12 seconds, then to delay for 3 seconds. I can see that it has already filled 19 rows of jars. And currently the conveyor is on, and it's waiting for those jars to be moved out of the path of the sensor. And I can see all this because I assembled it, I built it, and I know what each one of these indicators means in this particular context of this problem. Right? I know what each LED, what each display means. But that's not going to be the case for anyone else, except for you guys. You should know by now. Right? But to make this clear for everyone else, we need a control panel interface for this thing. And I think this is really easy to make with a laser cutter. Each one of these blocks will have a pattern, a cut pattern that is associated with it. I have the example here from the delay brick. So the red here represents the cut, and the purple pink color is just there. It's not like, there's no like laser power associated with it. I just have it there for alignment, so you can align them in a row. And so for whatever sequence of bricks you decided to assemble for your problem, you would copy the corresponding patterns into whatever software you're using, align them up in a row, and then with some other color for the cut, or was it the engraving power, or whatever it is, you would annotate what each one of those means, what each LED means, if that means that the conveyor is on, or that means that you've turned some motor on, or something like this. What each one of the displays means, if that's a time, or the time for the drip, or the time for the dispense. Just annotate everything pretty simply. And then you can laser cut that. Bolt all the blocks onto the back of it. I mean, when I say blocks, I mean bricks. I recently renamed it to bricks, and so it's still in my head. So you bolt all the bricks on the back of it, and I imagine you would just cut a big square out of the front of an enclosure and then bolt that onto it. And that would be it to create a nice, clean, professional-looking interface, or so I assume anyways. I haven't actually done this yet because these bricks are prototypes and there's going to be a lot of changing, so I don't really see a point in creating the interface and the patterns and all that for it. But it seems pretty straightforward. So this is revisiting those design goals again, comparing the two solutions and seeing how it's worked out. So I think I've covered a lot of these points already. But first off, I think it's more reliable. I think it's more reliable for really the most important part is that there's no application-specific software. So it's easy, it's reliable, and that makes it debuggable. It's debuggable because you can select, it allows you to debug really basically the same way. You can actuate and test each individual sensor in the same way. You just manually activate the output. But it also enables you to test the control software, to debug the control software, because now you understand what each of the pieces are, and there is no like MicroPython board with some mystery in it. There's no weird connections to some display, and it's repairable for the same reasons. You just cut out a block, put a new one in, and you're done. And I think it's a lot easier to use. Your whole display is in front of you. Everything that you need, every little knob. There's no menu. There's no anything. So I think it's better in almost every way. There's a few ways where it doesn't quite measure up. The first little thing is that the counter doesn't count the number of jars you filled. Of course, it counts the number of loop iterations. So you have to interpret that in the context of whatever you're doing. In this case, it means you have to multiply that by 4, and that's how many jars you filled. I don't think that's a problem if you don't give anyone the option. The other thing is that, so for example, in the previous solution, you had the option to configure the dispense time. So there's many different sizes of jars that you're filling, and you have like a configure mode where you can press the button and it dispenses wax. You can fill it up, like that's how full, and it times how long it spends to dispense the wax. And then times how long it just times to dispense it, and it can save that value for you like with a name. And so when you want to okay, now we're going to make the 7-day candles. So you just look up in the menu, okay, this is the type of candle I make, and you don't have to worry about anything else. You don't have to worry about the times. But in this case, you need to now have like a stopwatch and measure the time it takes to fill up the jar, and then maybe have like a sheet hanging somewhere that you write the times on it. And I think that is, in this case, perfectly reasonable and acceptable thing to do. First off, there's actually only like 3 different kinds of candles or sizes that you're making. So it's pretty easy to do. The wax fills slowly. There's no, okay, yeah, the wax fills pretty slowly. It's not like you really need a timer. You can just sit there by hand and do it. It's not a problem. And it's probably, in the long run, even faster for people to operate, because the people that do this are doing it all day. They're going to know, like, within 2 days what all the times are. They'll just do it by hand. Next candle, crank the switch, and they'll be done. Oh, I think that's a reasonable trade-off in this case. Yeah, some ideas of where to go from here. First off, make them smaller. Maybe it's like there's a lot of improvements that can be made. Right now, the software consumes about 5% of the space, so there's a lot of opportunities to use a smaller computer there. Mount all the pieces on the back, the non-displays on the back, stuff like that. I want a better interconnection method, because right now it uses male and female header pins, and so everything kind of connects together. And if you have a bunch of these on the back of the board that are bolted in, and you want to take the middle one out, and you unbolt that, you can't take it out because all the header pins are holding it in. So someone should suggest something better, because I'm not really sure how to do that, besides soldering it, but I'd like to avoid that. Yeah, so I'm probably going to keep this simple like this. I don't know how far I'm really going to go, but I imagine you could go a lot farther. You could have all these bricks auto-detect each other and automatically generate an interface on your computer that you could use to remotely interact with it, to monitor and control it. This would give you an Internet of bricks, of course. And that could be useful. I don't know. I don't think I'm going to do it. And if this like actually becomes useful, and I want to do more, and have lots of different kinds of bricks, I think it'd be useful to have just standard bricks, call them like stem cell bricks, like different types of bricks that you would then reprogram for your specific function. And of course, there's no need to stop at one-dimensional collections of bricks. You could go to 2D, or you could have little cubes. You could go to 3D. So then you can have 3-dimensional collections of these computing bricks, massive blocks and structures, 3-dimensional computing structures, or sculptures, really. I don't imagine it's being fun debugging, but I'd really like someone to do it, because I think it would look pretty cool. And if you noticed, these blocks, these bricks in this solution, it forms a chain. This is a blockchain, right? So the next time you're lighting up a prayer candle, remember, the blockchain brought it to you. If you want to, I'm putting this on GitHub, is where I've uploaded most of this. I've created a Hackaday project for it. I'm kind of new to this Hackaday project thing, so I've just created the page. If you are interested, I'm going to be updating it with further stuff. Yeah, and that's it, guys. Thanks for listening.